All right, so sections 2.2, 10.2, and 10.3 are all about conic sections. Conic meaning cone, and section meaning cross-section. So in other words, shapes you get by slicing a plane through a cone. So what we do is we take a cone, and we've seen cones before. We take a cone, something that looks like this, and we slice a plane across it. We slice a plane across it like that, and we look at the shape we get after we do that. And so there are several types of conic sections. What's kind of interesting though about cones is what we call a cone, a lot of mathematicians call a half a cone, because it turns out the cones we look at in this class are, we might call them a double cone. Because what they do is they actually are kind of two cones coming together like that, at the tip, like that. So that's kind of the shape we're going to be looking at. And what we have to do for some of our shapes we're going to be looking at is we have to envision the cone goes forever in both directions. So in other words, the cone just keeps getting wider down here, and it just keeps getting wider up here. So I know that's kind of hard to picture sometimes like this infinite double cone, but that's kind of the shape we need to think about for some of our cross sections that we're going to look at in class today. So there are four basic conic sections. There are four basic conic sections. And I actually, since my art skills are not the best in the world, I took the liberty of stealing a picture off the internet for this one.
Did you cite it properly?
What's that?
Did you cite it properly?
No, I didn't. No. You should report me immediately. Then I can go on fall break early. Okay. So these are our cross sections that we look at, everyone. And of course, we recognize the first two names. If you're not as familiar with the third and fourth name, that's okay. But we have parabolas, which we've already talked about. So we already learned about these, which is a shape you get by kind of slicing diagonally across a cone like this, but it kind of keeps going forever and ever and ever. And then you have a circle if you slice a plane across a cone. If you do it more at an angle, you get an ellipse, which is basically like an oval. And if you slice both cones, kind of like this, you get a shape called a hyperbola. And one of the most important things I can tell you about a hyperbola right now is that it is not two parabolas. It's actually a completely different shape. It looks, just from this crude drawing, you're like, well, Steve, it looks like there's a parabola, and then it looks over here like the hyperbola is just two parabolas. Is that right? And it actually is not. It's got a completely different shape. Not completely different, because they look kind of the same. But it does have a different structure than a parabola. So these are our conic sections we're going to look at. And just so you know, this is kind of what we do in section 2.2. This is what we do in section 10.2. And this is what we do in section 10.3. Which are the sections we're going to be covering over the next couple days, this week. Those three sections, circles, ellipses, and hyperbolas. So this will be today. This will be today and Thursday. And this will be Thursday and maybe finish after break. So maybe we'll have to do a little bit more cleanup on that one when we come back from fall break. So what do we know about these things? Well, if you just picture what they would look like when you graph them, it turns out that of all the conic sections, of all conic sections, only the parabola can be a function. The circle, ellipse, and hyperbola are not functions. They fail the vertical line test, and the equations have y squared in them. So those were kind of our two big ways to know if something wasn't a function, if it failed the vertical line test, or the equation had a y squared in them, or if you had a repeated y value with you had a repeated x value with two different y values. So just so we're clear, everyone, we're not talking about parabolas in this unit, but in case you're curious, there is another way to look at parabolas, and that's actually what section 10.1 is about, but we skipped that one because we've already covered parabolas. So that's why we're jumping straight into circles today. So it's actually kind of cool because Donald Duck, in the aforementioned cartoon, Donald Duck learns about slicing a cone to get different shapes, even though they never say conic section. They never say the term conic section in the cartoon, so they do slice a cone. And I'll show you this just for fun, it's a week before break, so. There's a part in the cartoon where Donald Duck is wandering through a forest, the mathematical forest. Look at this thing. And square roots. Yeah, he sees square roots on the trees. This thing is so big. Why didn't I shrink this down before class? This is a nightmare. Okay? People are going to get sick watching this video later. All right. Yeah, you can see him walking through the forest and he finds these square roots on the tree. So that, you got to say that's clever. Has anyone ever seen this cartoon before? Yeah. Yeah, it's a good one. They'll also teach you how to play billiards, and if anyone can follow that part of the cartoon, they win. Okay. Because it's nuts. All right, so to understand circles, you need two things. A circle is defined by two things: a center and a radius. A center and a radius tell you how to find a circle, because a circle is all points a fixed distance, radius, from a fixed point, the center. Which is exactly why we get this really cool mathematical tool in math that is, don't worry, I just got excited about doing pictures before class. They're not going to happen all day today. Apparently I don't know how to scale them before class. There we go. There's a compass. Now these things were awesome when we were allowed to have these in school, because what you had was you had the sharpest point ever that you could use to torture the people next to you, and you had a pencil that was always dull. No one ever had a pencil with a sharp pencil on their compass. I don't know what happened. And then what would happen was you'd jab the point in the paper, making a hole in it, because it didn't work unless you made a hole in the paper, and then you'd start drawing your circle, but inevitably what would happen is it would slip at the last second and you'd get something like that, and you never got a circle. And then what you'd do is you'd go borrow a plastic cup from the kitchen cabinet and just trace around that and say, there's my circle. Because these things were horrible to use, but they were a lot of fun. It's like the only weapon we were allowed to have in elementary school. All right, so if someone tells you a circle has a center of 2, 1 and a radius of 5, you can draw the circle. That's all you need to draw the circle. Now, there are infinitely many points on a circle, but we know how we draw graphs in this class. We graph a few simple points and connect the dots with an appropriate curve. That's how we always do graphs. We don't plot 300 points really close to each other and say, look what I've drawn. We draw like 5 or 6 points, and then we connect the dots. So that's exactly how we're going to draw circles also, everyone. So what are going to be the easiest points to plot? Well, we start by plotting the center of the circle at 2, 1, right there. And then every point on this circle is how far from the center? 5. So every point on the circle is 5 points from the center. So where are the easiest points to find?
0, 5.
From here, we're going to go, where are we going to go to get our points?
5.
Up 5. Let's go up 5. Where else are we going to go?
Right 5.
Right 5. Where else are we going to go?
Left 5.
Left 5 and down 5. 1, 2, 3, 4, 5. And remember, everyone, what you're doing is you're counting away from the center. And do not worry if you cross over one of the axes. You can cross, you can cross the x or y axis. But please move the radius distance up, down, left, right, which makes it sort of sound like an old video game code. Up, down, left, right, BA. Okay. Once you have that, you do your best to draw a circle. Now, how many points are really on the circle, everyone?
Well, infinite.
Infinitely many, but most of those points are irrational. Most of them are horrible decimals. Isn't that the case with almost every graph we do? So we don't bother to try and plot the other points, we just plot these points. And then for me, I'm not the best circle artist out there, but for me what I do is I try to do it 1/4 at a time. Some people blow my mind on the test though with how good they are at drawing circles. It's incredible. But there's our circle. Infinite points, 5 units from the center, which actually means, everyone, the center is not a point on the circle. Even though I plotted that point, that's not officially a point on the circle because it's not 5 units from itself. So really what the circle is just the loop. Not the inside of it, not the point in the middle, it's just the loop. Just the circle itself. And that's how we draw a circle. The main things people mess up when they're drawing these things is they get all freaked out when they have to cross over an axis. They think, do I start my count again? Nope. You just keep on counting to 5 in each direction in this case. Look okay, everyone? Is it a function? No, it fails the vertical line test. But does it still have a domain and range? Yeah. Not a function, but the domain and range can still be given. And if you've drawn a good graph, giving the domain and range is not that bad. This one seems to go from -3 to 7 on the domain, on the x-axis. And what does it do on the y-axis? -4 to 6. Each is twice as long as the radius. Use brackets, not parentheses. So I am not going to try and destroy you on the exam by saying your circle isn't perfect, because as you can see, my circle isn't perfect. But there are 3 things I will usually mark people off for on an exam with drawing circles. 3 bad circle techniques that cost you exam points. I actually have names for them also. I call them the miss diamond and the clover. And these are the things I see people do on a test that will cost them points when they're drawing their circle. If I see someone that draws a circle like that, where they just don't even bother to hit the points, I'll take off points for that. If I see someone that puts no effort at all into trying to make their circle round and just does this, I'll usually take off points for that. And then the other side of that is someone who tries to make it just too round and does this. Other than that, I'm pretty lenient when I grade your circles, because I know they're tricky to draw. All right. Since we need the center and radius to sketch a graph, we need to be able to determine center and radius by looking at the equation. If the two things we need to draw one of these are the center and the radius, then there needs to be a way to look at the equation and just pull the center and radius off of it. So, here is an example of an equation of a circle. One second. Here's the example of an equation of a circle. This is actually the circle that we just drew on the previous page. So look at this, everyone. Look at this equation up here. This is the circle we just drew on the previous page. The circle we just drew on the previous page had a radius of 5. Do you see anything in there that could clue you off to the radius being 5?
25.
The 25. So what do you have to do with that number? You have to square root it. So this right here, everyone, is the radius squared. That's what that number is. That's whatever your radius is squared. Do you see anything that tips us off that the center of the circle was at 2, 1?
The X and Y positions.
Yeah, the numbers next to the X and Y. What do you notice about them, though? They seem to have reverse signs for what we think they might have. Does everyone see that? So what happens is, this number right here, and this number right here, change the signs to get the center. The X value is with X, and Y value with Y. So we get the center of 2, 1. So the equation does give us the radius and the center. We just need to know two things. We need to take the square root of that number to get the radius, and the coordinates for the center are in here. They just have the opposite sign in the equation from what we use when we draw our graph. So this is what it looks like, everyone. I copied this from the book just to be a little bit professional here. A circle with center hk and radius r has this equation: x minus h squared plus y minus k squared equals r squared. We see the squared right here. So that means the radius is r. And we see the minus signs in here. And that means our center is hk. Just like that. So if someone gives us an equation, we can certainly draw the circle for it. The other thing we could do is if someone gives us the center and the radius, we could write the equation ourselves. We just need to go backwards. Are we okay so far?
So they'll always go in the y at the x2 and y2 spot?
Oh, I see. You're kind of thinking like of a line, if you will. Yeah, yes, they do. This is actually based on a formula you already know. Has anyone ever seen this before? We have something squared plus something squared equals something squared.
Pythagorean.
Yeah, it's actually based off the Pythagorean Theorem, which is actually the distance formula. So this is based off the distance formula. That's based off the distance formula, where your radius is like the hypotenuse, good for me, I can't remember how to spell hypotenuse, of a right triangle. So this does come from somewhere. This is based off the Pythagorean theorem. So let's do a little drill real quick, everyone. Let's do a little drill. Circle has a center of 4, -5, and radius 9. Give equation. Everyone give the equation of that circle for me. Everyone give the equation of that circle. There we go. That helps you. If you get this, you're well on your way. If you don't get this, we'll get them next time. What should I put in my first set of parentheses? X minus 4. Very good. What should I put in my second set of parentheses? Y plus 5. And what goes on the other side of the equation? 81. Good. All right, everyone. Does everyone see where that came from and either get it right or they know why they got it wrong? Are we all right? In the back, everyone okay? All right. Try this one. Give center and radius from equation. I am trying to mess with you a little bit, so don't freak out. Give the center and the radius from the equation. Don't worry, it's not a test, so take a guess, even if you're not sure. And you don't need a calculator for this. You can just, if you think you need a calculator, just leave it how you think. Just leave it how you would put it into your calculator. What's our center for this one?
0, 0.
It is going to be 0, and what's the y value going to be? -2. Everyone see why it's 0? Because there's nothing getting added or subtracted from 0, so or x, so we just assume it's 0. And I know it's not a nice number, but what's the radius exactly? It's the square root of 5. Because the equation has x squared in it. I'm sorry, has radius squared in it. So therefore, if you want to get the radius, you have to take the square root of that number, even if it's not a number you want to take the square root of. All right, let's draw one. All right, everyone, do me a favor. That's not what I want to do. Do me a favor. We're going to draw this circle, which you'll be able to see again in just a moment. We're going to draw that circle, and after you draw the circle, give the domain and range of the circle. Do your best. I know you might not have graph paper with you today or a grid. Just do your best. A good way of knowing that if you got your points in the right place is making sure you can give the correct domain and range. That's why I ask you to give the domain and range, because that's a good way for you to double check and make sure you do your graph correctly. And then when you're all done, take a look up here and see what you think. Are we winning or losing today? You doing okay over here? So, they do give a formula for the domain and range, but I think it's such a pain in the neck to learn the formula that I don't bother to teach it, but I'll show it to you just in case you're interested. Really what your domain is, everyone, is your domain is given by, oops, and your range is given by this. And I truly do believe, all right, everyone, I like cut my arm. We're taking a quick break. I'll just double check. So did everyone get the circle okay? Everyone doing all right with this? Everyone got the center in the right place? Took the square root to get the radius, so you weren't trying to draw with a radius of 9? And the domain and range, I think the easiest way to get it is by just looking at the circle you drew. But there is a formula for doing it by adding and subtracting r from h and adding and subtracting r from k to get the range. But I think it's easier just to do this. Let's talk about this for a second. No one said anything out loud yet, because I want everyone to have a chance to think about it. But I want you to just look at those and decide for yourself on your paper, not out loud, but on your paper, why each one of these is not a circle. Jot down on your paper why each one of those is not a circle. Don't say it out loud, because I want everyone to have a chance to think about it. None of those are circles. This is not a trick question. None of them are circles. And you're going to write down what tips you off that you know you're not looking at the equation for a circle. Why is the first one not a circle? No squareds. No squared. So this is a line. That's actually a line, not a circle. Because the squares aren't there. Why is the second one not a circle? It's subtracted, yes. So minus instead of plus, this is a hyperbola, which we will learn about in section 10.3. Not today, but we'll learn about that next time. Why is the last one not a circle? Yeah, you can't have a radius squared be a negative number because the radius can't be imaginary. So this is a negative 81 because r squared equals negative 81. Nope, can't have that. This actually is nothing. It has no ordered pairs. If you were to graph that, it would just be a blank coordinate system because there's no numbers you can put in there that will make that true. Because you can't add a positive number to a positive number and get a negative number. So just be aware of that our circles do need to look a certain way, and it's very, very easy to slip in something that is not a circle. The most difficult thing for us in section 2.2 is when the equation is not given in the form when they don't give it to us like that. Because if they don't give us the equation like that, it's a lot trickier. Now, have we ever seen that before where there's two different ways to give an equation for something? For instance, so there are two different ways, or maybe even three different ways to give the equation of a quadratic. Yeah, recall quadratics. Those are not all the same equation. That's why I call one FG, one H. They're not all the same quadratic. But are those all quadratics, everyone? Yeah, and depending on which form they give it to you, one of them might be easier to work with than another one. So what we need to be aware of is that circles can come in a different form. This, everyone, is a circle. This is not a trick. This is a circle. It's just not given to us in the form we're used to seeing it, and the center and the radius are hidden. You cannot get the center and the radius just by glancing at this. I'm not saying you can't do the mental math to find it on your own, but I will say just by looking at this, the center and the radius are not right in front of us. So we're going to find it. We're going to find the center and the radius of this circle. What I'd like everyone to do is I like to rewrite this so it says x squared plus 10x, then leave a space and put plus y squared minus 6y, then leave a space, and we're going to subtract the 9 from both sides. So all I'm doing, everyone, is rearranging the terms. I'm putting the x's together, I'm putting the y's together, and I'm moving the number to the other side. Everyone okay so far? Now look very carefully and listen very carefully to the question I'm asking. What is the number in front of x, not x squared? 10. The number in front of x is 10. Everyone with me? Okay. Jot that down, kind of one line down here. What is the number in front of y? Negative 6. All right. Take this number 10 right here. Cut it in half. What's half of 10? 5. Now square that. What's 5 squared? 25. Take the negative 6. Cut it in half. What's half of negative 6? Negative 3. Square that for me. 9. So what you do is you half it, then you square it. Half it, square it. Now take these two numbers, this 25 and this 9, and add them to both sides of the equation, like this. X squared plus 10x plus 25 plus y squared minus 6y plus 9 equals negative 9 plus 25 plus 9. What I'm doing is I'm adding a 25 to both sides of the equation, which is fine, you're allowed to do that. And I'm adding a 9 to both sides of the equation, which is fine, you're allowed to do that. Anyone know what I'm doing right now? What is this called, what I'm doing right now?
Completing the square.
Yeah, it's called completing the square. This is called completing the square. I'm just doing it on two variables at the same time. Does this sound familiar to everyone? Take the number, cut it in half, then square it, and then add it to both sides? This is completing the square, everyone. And what we're doing is we're completing the square so we can get this thing into the form where we can see the center and the radius. Now, Look at that number there, and look at that number there. Those tell you how to factor your x's and how to factor your y's. How does this whole thing factor right here, according to completing the square? What should that factor to?
X plus 5 squared.
X plus 5 squared. How should that whole thing factor according to completing the square?
Y minus 3.
Y minus 3 squared. What's negative 9 plus 25 plus 9?
25.
Is it possible to see the center and the radius now? Everyone write it down. That is pretty much the hardest thing you have to do in this section, is complete the square. Which is exactly why, before we go to break, you're going to do another one on your own. Sound okay?
Yep, fine.
Anyone have any questions before you try one on your own? All right, here we go. This is what I want you to do for me, please. It's going to be a long problem. Give center and radius. Graph the circle. Give domain and range. And answer this question. True or false? The center is a point on the circle. Do this on your own, everyone. Do not do it out loud. Try this on your own. It is okay to make a mistake. It is okay to mess up. And I am not giving you the world's worst completing the square problem to do. So if you're getting horrible, nasty decimals or fractions, check your math. So class, if we complete the square on this circle, we can find that the center is at -3, -2. And we get a 1 on the other side, and that means that that's the radius squared. So the radius is just 1, because the square root of 1 is 1. So it's a very tiny circle. And then if you sketch that little circle, you can see that the domain is -4 to -2, and the range is -3 to -1. And it is false that the center is actually a point on the circle. The center does help us draw a circle, and I would never really try to draw a circle without using the center. And you don't need to erase it, but just be aware that the center is not actually a point on the circle. It's just a reference point we use to help us draw the circle. We're not quite done with circles yet, but does anyone have any questions about this example up here? I know I asked you to complete the square very fast after showing it to you, so it's okay to have questions. Does anyone see anything up here that is disturbing them? So let me make a few more remarks about circles. What we kind of have is we have what we call the center radius form of a circle, and then we have the general form of a circle. Now, this one is much more useful, the center radius form, because that's what the form we turned it into, so we could get our center and our radius. That's why it has that name. The general form was the form that we started with. So the general form would look like this. X squared plus y squared plus 6x plus 4y plus 12 equals 0. And what we learned, everyone, is that to go from the general form to the center radius form, you complete the square. But unfortunately, every now and then, they want you to go from the center radius form to the general form, which I think is silly, but it's not a bad mathematical skill to have. And you do that by multiplying and collecting like terms. So every now and then, they will give you a problem where they ask you to turn the center radius form into general form. So, turning center radius form into general form, which is not the worst thing in the world, it just takes a little bit of time. So let's say you know this is the equation of your circle, and you love this equation of the circle because when you look at this form of the equation, you can immediately get your center and your radius. For instance, where is the center of this circle, everyone? -3, 4. And what's the radius? 7. It's awesome. But if for some reason they start like nagging you and saying, nope, we want it in general form, then what you have to do is you have to FOIL this out, which will give you x squared plus 6x plus 9. You got to FOIL this one out, which will give you y squared minus 8y plus 16 equals 49. Then what they want you to do is they want you to write the x squared first, then the y squared, then the x, then the y, and then they want you to collect all your constants together and combine them into a like term, which in this case would be -24. That looks right. And I won't lie to you, everyone, I actually don't see much of the point in that because there's nothing this thing tells me that this one doesn't tell me. So I'm like, why would I ever do that? That doesn't give me the information I need. But you will notice when you do your homework that some of the homework problems will ask for the circle in both forms. So you do need to know how to go both ways. Everyone okay with that then? I think it's harder to go the other way, completing the square. This way just takes some time. Let's do one more complete the square problem. So this is a circle. This is a circle, it just looks really, really bad. The numbers in front of x squared and y squared need to be 1. If they are not, divide every term by that number. If they are different, it is not a circle to begin with. So everyone, in order to complete the square, you cannot do it unless the numbers in front of x squared and y squared are 1. So you have to divide every term by that number that's in front of them. And if they have different numbers, if like one of them had a 4 in front of them, the other one had a 5 in front of it, then it's not a circle anyway, so it's not a problem we'd be doing in this section. So it's okay. They should always be the same. If you can't reduce to an integer, don't reduce. After you do your division, if it's impossible to reduce it down to an integer, you actually should not reduce it. And I will show you exactly what I mean by that, everyone. So what am I about to divide everything by?
4.
We're going to divide everything by 4. Is everyone cool with that? Everything gets divided by 4. What's 4x squared divided by 4, class? X squared. What's 4y squared divided by 4? Y squared. What's negative 28 divided by 4? Negative 7. And we can reduce that all the way down to an integer, so we do. We make that negative 7x. 36. Can we divide 36 by 4 nicely? 9. Good. Can we divide 14 by 4 nicely? No. So this is what I mean by this, everyone. If you can't reduce it down to an integer, don't try to reduce it. I do know I could rewrite that as 7 halves. But it turns out it's going to be in your best interest not to do that usually. So our first step was to divide by 4. Now we gather the x's together. We gather the y's together. And we move the constant over to the other side. This is just like the completing square problems we just did, except the numbers are worse. And that makes it harder. And I know it makes it harder. We'll call this step sorting. We sort the equation. Now, to complete the square, I need to take the number in front of x. What's the number in front of x, class?
7.
Careful?
Negative 7.
-7. I divide that in 2. I cut it in half. This is how you cut that in half. You put a 2 underneath it. Then I square it. And much to my disgust, I get 49/4. I'm not too happy with that, but that is what I get. I take the 9. How do you cut 9 in half? What do you write? 9 halves. Leave it as a fraction. It'll make your job a lot easier. 9 halves. I square 9 halves. What does that become when you square it? Not double it, square it. 81/4. Divided everything by 4. I did a sort. I complete the square. Now I add 49/4 and 81/4 to both sides. Keep it together, we're almost there. Is it difficult to factor the left-hand side if you've been showing your work? Not if you've been keeping track of your work, it's not. If you've been keeping track of your work, you might remember from earlier today when we did it, and from when we first learned how to complete the square, that these two numbers here show you exactly how to factor. The factoring is not a mystery. It looks like it's going to be awful, but it's not a mystery. It's x minus 7 halves squared plus y plus 9 halves squared. And over on this side, I have 14/4 plus 49/4 plus 81/4. This is exactly why we keep our fractions like the way we did. Because I can add those fractions. Because I can do 14 plus 49 plus 81. And I get 144. Over 4. What is 144 over 4? 36, isn't that convenient for us? You don't have to love it, but can we get the center now and the radius? Yeah, we just got to remember to change the signs. Center is 7 halves, negative 9 halves. Got to remember to switch the signs from what you see in the equation. And the radius is 6, and we're done. Not every problem in the homework requires you to complete the square, but was going to say you have to complete the square on a circle, but that doesn't sound right. Here's a circle, complete the square. Tell that to someone, give them a headache. Yeah, you'll probably need to complete the square on the exam. All right. Last thing on circles is this. The most important circle is actually also the easiest circle, I think. The easiest circle you can draw in this class is the most important circle. It looks like this. Can anyone tell me what the center of that circle is?
0,
0,
0.
0. Can anyone tell me the radius? 1. It looks exactly how you'd think it looked. It is centered right at 0, 0 and has a radius of 1. It's got a special name. It's called the unit circle. And if anyone here is taking pre-calc next semester, you're going to hear about the unit circle over and over and over again, because they'll do crazy, wonderful things with it. The unit circle is used in trigonometry all the time, which is what we call pre-calculus here. All right. Okay, that will move us into 10.2. The ellipse. And the ellipse is what we often call an oval. It's what you often call an oval. In this class, we have two kinds of the ellipse. We have the, well, this one I kind of call the short and fat, or I call it the horizontal. And this one I call the tall and skinny, or I call it the vertical. And because I am Steve, I also occasionally call this one the Ernie. And what do I call the other one?
Bert.
I call the other one Bert. For those of you who don't know what I'm talking about, first of all, I'm kind of hurt about that you don't know what I'm talking about. But if you don't know what I'm talking about, that's okay. But you got these two Muppets. They're best friends. They appear on Sesame Street. They're pretty cool. And Bert's head is kind of tall and skinny, like an ellipse. There's Bert. There's Ernie. So it is actually perfectly acceptable in this class, if we're taking a test, to refer to them as the Bert and Ernie. Just don't confuse your Muppets, because that just destroys me. But for those of you who prefer to be a bit more precise, that's okay. You can call this one the horizontal ellipse and this one the vertical ellipse. That's fine also. You do not need to use the common Muppet name. So we're going to learn how to draw these oval shapes, these ellipses. In Math 121, our ellipses are all centered at the origin, 0, 0. Even though our circles could have the center anywhere. So the circles that we spent the first half of class today doing, those we could center anywhere like we were doing. We put the center all over the place. These, however, these ellipses, these oval shapes we're going to be drawing, for this class we're always going to keep them centered at the origin. Why? Because this is the introduction to ellipses. You want to learn more about ellipses, you take the class after this pre-calc, and they'll teach you a lot more about ellipses. Today, and a little bit on Thursday, we're just going to kind of get our feet wet with the ellipse, see what it's all about. All right. So, every ellipse that we draw in this class will either look like this or like this. And the center is always 0, 0 in our class. Always. Because these are ellipses, not circles, there's always a long way across and a short way across. So if you put the center right there, then what you have is you always have a long way across the ellipse and you have a short way across the ellipse. There's always a long way across and a short way across through the center. If you look at the long way across and you look at where it stops when it hits the ellipse, each one of those is called a vertex. Same word that we used for a parabola, except these have 2 of them. And if you're talking about more than one at a time, you actually refer to them as the vertices, not the vertexes, although I've been known to say vertexes sometimes. But they are actually called the vertices. Every ellipse has 2 of these vertices, just 2. Just 2. They don't have them when you go across the other way. The long way across is called the major axis. The major axis is always the long way across. It changes from ellipse to ellipse, whether it goes up and down or left and right, depending on what type of ellipse you have. But the major axis is the long one. And thankfully, there is something that makes sense in this class. The small one is called the minor axis. And the length of the major axis is always greater than the length of the minor axis. So it doesn't matter which way it goes. What matters is which one's longer. That's how you know which one is which. Not which one goes up and down, not which one goes left and right, but whichever one is longer you call a major axis, whichever one is shorter you call a minor axis. The endpoints of the minor axis are called endpoints of the minor axis, not vertices. The vertices are only the endpoints of the major axis. The endpoints of the minor axis, yes, I did write that on purpose, are called the endpoints of the minor axis. They do not have a special name. How do we draw circles? We found the center, and then how many points do we find to help us draw a circle? 4. Let me ask you this. Do you think if we knew where the vertices were, the endpoints of the major axis, and if we knew where the endpoints of the minor axis were, we could draw a pretty good ellipse? You think that would be enough to kind of connect the dots and make an oval for ourselves? And that's exactly what we're going to do, class. That is exactly what we're going to do. We will locate the 2 vertices and the 2 endpoints of the minor axis and sketch an ellipse. That is exactly how we will draw them. We will locate the 2 vertices and the 2 endpoints of the minor axis, and we will sketch a picture of an ellipse. Sound okay? Let's do it. Draw an ellipse with vertices at 0, 6, 0, negative 6, and endpoints of the minor axis at negative 3, 0, 3, 0. Draw an ellipse with vertices at 0, 6, 0, negative 6, and endpoints of the minor axis at negative 3, 0, 3, 0. That's how we draw an ellipse, everyone. I'm not the best at drawing these either. You just do your best. Make your ellipse. And then after you've made your ellipse, I know it's not a function, that's okay. See if you can jot down the domain and range of the ellipse, or if you didn't get it drawn, because you know you're going to draw it later because I go too fast for you, see if you can do the domain and range from my graph. Yeah, it's not a function, because it fails the vertical line test. That's okay. That doesn't mean you can't give a domain and range. You can still look at how far to the left and right it goes. You can still look at how far up and down it goes. You can also answer some other questions about it, like this. Length of major axis, length of minor axis. You can also answer those questions. That's not even an ordered pair or an interval, that's just going to be a number. Like if you dropped a little line segment in there, how long would it be? How long is the major axis altogether? 12 units long. How long is the minor axis altogether? 6. So we can answer a lot of questions about one of these once we get the picture down. And we can get the picture down as long as we know where the endpoints of the minor axis are and the endpoints of the major axis are. So, class, let's learn how we can look at an equation for an ellipse and get this information up here ourselves without someone just telling it to us. Are we okay so far? Oval shape here, the ellipse. Oh, one more question real quick. How many ordered pairs are actually on the ellipse? Infinitely many, even though we only used 4 to graph it. Does everyone agree with that? Yeah. There are infinite ordered pairs. We used 4 to sketch a graph. We've been doing that all semester. The first time we drew a parabola, I plotted maybe 5 or 7 points. Even though a parabola has infinitely many ordered pairs, we don't plot infinitely many ordered pairs. We plot several, then we connect the dots. Okay. This is an ellipse equation for an ellipse with any center, not just 0, 0. This is what the equation looks like for an ellipse. Where the center could be anywhere. And you do see a lot of variables in there, everyone. X's, Y's, H's, K's, A's, and B's. But that number over on the right is a 1. It is just a number 1. This is what we would let them look like if we can move the center everywhere. And you should actually kind of see where the center is based on what we did with circles. Still got that H and K in there. But in Math 121, since our center is 0, 0, our equation looks like this. Which is a little better. X and Y are X and Y. The number 1 is the number 1. A and B are the secret to finding our 4 points. The numbers you see under X squared and Y squared are the secret to finding our 4 points. And a little tip for everyone, they actually have to be 2 different numbers underneath those. We call them A squared and B squared, and they do have to be 2 different numbers underneath. I'm going to show you how to look at one of these equations and almost immediately know how to draw an ellipse. It is not going to be the worst thing you've ever seen. Where are all of our ellipses going to be centered? 0, 0. So we got to know this. We got to know how far to move up, down, left, and right. Does everyone agree with that? We're going to get our 4 points. Here's how we do it. Take the square root of number under X squared. Move that many left and that many right. Take the square root of number under Y squared. Move that many up and that many down. This will actually give you 4 ordered pairs on the ellipse. The secret is taking the square root of the number under X squared, the square root of the number under Y squared, and that will tell you exactly how far to move up, down, left, and right to get 4 exact points on your ellipse. Every single time this will work. Every single time. So, that's an ellipse, everyone. This generates an ellipse. I'm wondering if, following my instructions, you can come up with 4 points on this ellipse for me. Everyone see if you can get 4 points on that ellipse by following my instructions. They're right up there. Right up here if you didn't get it written down, because I know I go fast. Just like that, you get 4 points on the ellipse. Just like that. How many points are actually on the ellipse? Infinitely many. How many do we need to help us draw it? Just 4 will help us draw a pretty good drawing. We use 4 points to sketch an ellipse with infinite points. This is not mathematical magic. It is a cool shortcut that helps us. For instance, Let's label these 4 points that we use to help us draw this. What's this one right here? Negative 5, 0. On the other side? 5, 0. Up on top? 0, 3. Down on the bottom? 0, negative 3. These 4 points, along with infinitely many other points, are all on the graph of our ellipse. And what makes a point be on the graph of the ellipse? The fact that it satisfies the equation. These points all make this equation true. Check it out. Negative 5, 0. Negative 5, 0. I plug negative 5 in for x into the equation. I plug 0 in for y into the equation. What's negative 5 squared? 25. What's 0 squared? 0. We will end up with 25 over 25 plus 0 over 9 equals 1. 25 over 25 is 1. 0 over 9 is 0. 1 plus 0 is 1. These points work. This is not just some sort of magical hand waving. It's a cool trick that helps us graph it. But really what we're doing is we are finding 4 points, the easiest 4 points to find, that satisfy this equation. All those points do. Every single point. Most of them are irrational. So it's not like we're inventing new rules for graphing. We're using a new technique because it works really, really well. That's what we're doing. The homework often refers to these 4 points as the x-intercepts and y-intercepts. Of the ellipse, because they're on the axis. So they actually are where it hits the x-axis and the y-axis. So this one right here, the x-intercepts for this one would be plus or minus 5, 0. And the y-intercepts would be 0 plus or minus 3. So rather than just saying, tell me 4 points on the ellipse, what they'll often say is they say, tell us the x-intercepts and the y-intercepts. But before that spooks you, remember those are exactly the same 4 points we are talking about. The x-intercepts and the y-intercepts. All right. How are we doing? We okay? Oh, by the way, one more thing on this one. I'm sorry. Which ones are the vertices? Why?
Because that's on the major one.
Good, because it's the longer one. That's it. Yes. So that right there is a vertex, and that right there is a vertex. The other ones are not. Vertices are only at the endpoints of the major axis. Okay. A squared cannot equal b squared, because if they were equal, we would have if they were equal, what would that be? That would be a circle. Yeah. You'd multiply both sides by 16, you get x squared plus y squared equals 16. We would have a circle. That's why I said the numbers underneath x squared and y squared have to be different. If they're not different, then we have a circle. One of them could be an invisible 1. Doesn't really look like an ellipse because it's not a fraction, but this could be rewritten as x squared over 1 plus y squared over 9 equals 1. So one of them could be an invisible 1. That's okay for an ellipse, to have an invisible 1 underneath there. They could, well, that's not the best way to say that. We might not have perfect squares. case, we just do the best we can. If they're not perfect squares, we still have to take the square root of them to find out how far we go left, right, up, and down. So even if they're not perfect squares, which is annoying, we won't do a whole lot of these, but if they're not, we still are forced to take its square root. And then you use a calculator to get a decimal approximation of how far you should go. Everyone okay with that? And finally, and this might not seem that important, but this is also something we need to say. Of the two numbers, which are always going to be different sizes, a squared is actually the bigger one. A squared is the bigger one. So when someone starts talking about a squared and b squared, they actually mean the smaller number and the bigger number. Always. A squared is always bigger. The reason we say this, because you might say, Steve, why does it matter which one's bigger? Why does it matter which one's a squared and which one's b squared? Is because people like to do this. They like to say this. Because they want to say that the length of the major axis is 2a, and they want to say the length of the minor axis is 2b. Now, if you don't like that, I'm going to demonstrate how that works in this next example, so don't worry about that, because I just gave you a lot of information here. So we're going to look at an example here together. All right, everyone. The cool thing about these ellipses is if someone's not asking you any extra questions about it, they're actually pretty quick to graph. They're pretty quick to graph. Because the number under x squared always tells you how to move left and right. The number under y squared always tells you how to move up and down. So for this particular one, when I draw my graph, I got to take the square roots of those numbers. So the square root of 4 is 2, and the square root of 36 is 6. So that tells me I'm going to move left and right. How many units in each direction?
6.
Left and right?
2.
2. Up and down?
6.
And I get my ellipse just like that. Just like that. Simply by looking at those numbers. You see, I don't even need to know which one is called a squared, which one's called b squared. I don't care which one's bigger. All I care about is that I'm moving left 2 and right 2, up 6 and down 6, and then I connect my dots like this. And I get my picture, and I'm done. But if someone wants me to get a little bit more into it, then I say this to them. A squared is 36, and b squared is 4. How do I know which one is which?
Major axis.
What's what?
A squared is always
A squared is the bigger one. You got two numbers there. A squared is always the bigger one. A is 6. B is 2. This is what I was talking about, everyone. Look at your picture. Look at the picture and tell me how long the major axis is.
6.
12.
12. Length of major axis is 2 times A, which is 2 times 6, which is 12. It's double the square root of a larger number, which is a nasty way of saying it, but that is how it works. Look at the picture. How long is the minor axis?
4.
Left to right. Yeah, it's 2 times B, which is 2 times 2, which is 4. Yeah, the most important thing is that can you draw it, but if they start asking you these questions like the length of the major axis, the length of the minor axis, or what's A, or what's B, or what's A squared, or what's B squared, we have to be able to answer those questions as well. We have to be able to answer those questions as well. If they ask me for the vertices, how many ordered pairs am I going to list? Just 2. Because the vertices are only the endpoints of the major axis. Does everyone agree with that? So the vertices for this one are 0 plus or minus 6. Up and down 6 units. Those are the vertices. All right. So we can go the other way also. Oops. Oh, I already got it. Running out of time. Edit, paste. Everyone, give me the equation that created that ellipse. Give me the equation that created that ellipse. If you don't know where to start, that's where I start. Think to myself, I'm writing the equation of an ellipse. The equation of an ellipse is always x squared plus y squared with numbers underneath them equals 1. I guess I just need to figure out what numbers go underneath them. Then I come over here and I do this. And look at the numbers and how far I went left and right and how far I go up and down. And then I make a rookie mistake. Those of you who got it right, can you see why I would make that mistake? I just get overexcited. I see that 7, I see that 3, but that's not the right answer. So I cross that out. Then I like to say, oh, that's right. I'm the best. Is that right? No, you don't double them either. You don't double them. You square them, so you get x squared over 49 plus y squared over 9 equals 1. The only question is, how did I know where to put the 49 and how did I know where to put the 9? Because I went left and right 7 squared under x squared. Because I went up and down 3 squared under y squared. At no point in doing this do you actually need to know which one's called a squared and which one's called b squared. You just need to know left and right helps you find the number under x squared, and up and down helps you find the number under y squared. But no, don't double. Square them. And that's how you figure out which number goes which place. All right. An ellipse has a minor axis that is 12 units long and vertices at 0, -10, and 0, 10. An ellipse has a minor axis that is 12 units long and vertices at 0, -10, and 0, 10. Let's give the equation. This is not a trick question. It might look like a trick question at first, but it's not. This is a real question. And my thought process when someone says this is this right here. I need to know the two numbers that go under x squared and y squared. It can often help to draw a simple, maybe not award-winning, but simple sketch. We just go like this. Oh, I'm clearly going up and down 10. And if that whole thing is 12, then I'm going left and right 6. So, x squared over 36 plus y squared over 100. Does a simple sketch help? I think it does a lot. We are out of time.